welcome to the 3.9 notes. We're going to be looking at derivatives of exponential and logarithmic functions. And so I'm going to start off with a couple rules, and the rules themselves are important to memorize, and then we'll talk about how to use them. And one thing I definitely want to be just upfront with you guys about is the importance of the chain rule is going to be key as we look at using the derivative rules with these different types of expressions. So I'm going to start off with a generalized expression for an exponential function with some base a. So if base is if the base is a, so a is some constant, then the derivative for this would be the natural log of the base times the same exponential expression as we originally started with. Now you might need to multiply that by the chain rule if you have a function within a function, which would occur up here in the exponent. And we'll practice that. Now, there is also a modification that we could look at specifically when the base of the exponential function is e. Now, keep in mind, exponential functions have your variable as the power, and we have a constant for the base. But if that constant base is e, then the rule is still the natural log of the base times the original exponential function, but the natural log of e is just 1. And so this is why you guys have already seen this pattern. The derivative of e to the x is e to the x. I'll add that in here. So e to the x is its own derivative. And basically the reason that that happens is because at any x coordinate, the slope is actually the exact same value as the output for e to the x, which is kind of a cool thing to think about. And we're also going to be looking at logarithmic functions and looking at the derivative rules for logarithmic functions. So we'll start with a generalized rule for any base. So I'm going to write this as log base b of x. Log base b of x. And this is going to be the derivative of 1 over the natural log of the base. So even though this was originally log base b, and it wasn't starting off as a natural log, we have a natural log in our actual derivative rule, and then times b to the x. So it's kind of times just plain old x, times the argument x. So this right here is the same as this argument. Now we might have the chain rule happening in this problem, and we're going to work a little bit more with how to handle that. But I'd like you to notice that both the derivative of an exponential and the derivative of a logarithmic function have a natural log of the base as part of the answer for that derivative. If we look specifically at the derivative of a natural log, and keep in mind a natural log could be rethought of as log base e of x. Well, then for that derivative rule, again, it's going to follow the same pattern as the generalized derivative rule for a logarithmic function. It'd be 1 over the natural log of the base, which is e, times the argument, which is x. But the natural log of e is 1. So we end up with 1 over x as the derivative with respect to x of the natural log of x. So this one is worth memorizing because it shows up so often. So these are the 4 rules that you're going to want to become very familiar with, and you're going to want to get memorized. Okay, now let's see how this might look with the chain rule. And sometimes kids struggle a little bit to identify the chain rule in these problems. And so what you want to look at is you want to look at the argument of the function. And if the argument of the function is just x, then you don't need to think about using the chain rule. But if it's something other than x, 3x, x squared plus 5, something else like that, some modification of x for the argument, then you are going to need to think about using the chain rule. Now, one other thing that's useful is you might be able to avoid the chain rule with some log functions by using properties of logs. So, like for example, number 1, we're going to do number 1 twice. So for number 1, by the way, this squared is for the argument. If we were squaring the entire natural log function, we would have parentheses here like this. Without the parentheses, you should assume that it is the argument here being squared. So I'm going to do this problem twice. The first time I'm just going to go ahead and use the derivative rule. So for a natural log, what we want to do is and if you can look up here a little bit, in order to see that this is going to be 1 over the argument, right here, 1 over the argument, which in this case is x squared. So I will do 1 over x squared, because the form of this problem is the natural log of something, okay? So then it's 1 over whatever we're taking the natural log of. That's how we are going to do this derivative rule. And what we're taking the natural log of is x squared. However, we have a function within a function here, so we need to multiply by the inner function's derivative. And when you multiply by something, you would multiply that on the numerator. So this would now be 2x on the numerator. And so when I simplify this, I can divide out an x on the numerator and the denominator, and I would get 2 over x. There is actually an easier way to do this problem, and that's to start by rewriting this problem with properties of logs. One of your properties of logs says that if there is a power for the argument, you can go ahead and make that power, rewrite that power as a coefficient for the whole expression. So we could think of this as y is equal to 2 times the natural log of x. Then y prime would be 2 times the derivative of the natural log of x, which is 1 over x, which is going to be an easier thought process. We didn't actually have to use the chain rule here. Number 2. And if you are feeling confident, pause the video, try a handful of these, see how you do on your own. All right, so the derivative of e to the x, and the main rule here is e to the power of something. All right, we do have chain rule because this argument here, this power, is actually a function within a function. But I'm going to use as my main rule e to the x, and so it is its own derivative. Now it's going to be e to the power of 3x, because with the chain rule, you've got to keep that inner function in there as part of the derivative. And then times the derivative of the inner function. This 3 should be written in front as a coefficient. So this would be 3e to the power of 3x. And this one, this pattern here is a good one to memorize. You could just pull that 3 in the front right away when you see that chain rule. For number 3, this is an exponential function with a base that's not e. So the main form is 4 to some power of x. And so for the derivative is the natural log of the base, which is 4, times the original exponential function. And I do have a function within a function right here, so I need to multiply this by the derivative of that function, which is 5. That 5 should be written in front, and other than that, this is an odd-looking answer, but you should not write it. You should not worry about trying to simplify it more than that. Just a point, sometimes people try to multiply these together. You can't do that. One of these is a base of an exponential function. The other is part of a natural log. You also cannot multiply this 5 times either of those 4s. These are all different types of numbers and measurements, and we cannot combine them further. We could write them in a different form, but it's not going to be worth your time to do that. Number 4. So again, our main form here is e to some power. We are going to need to consider the chain rule because there's a function within a function. The derivative of e is the same function as we started off with, including evaluated at the inner function. And then by the chain rule, I need to multiply this by the derivative of the inner function. Let's use the power rule. I like to write that in the front of the expression. This is probably the most common way you would see that written. Number 5. Now, there is a difference between number 5 and number 1. In number 1, the argument is being raised to the power of 2. In number 5, the entire expression is being raised to the 4th power. These are very different problems, although they look similar. Man, the power of the parenthesis is evident here on this problem. You cannot use a property of log to try to move this out front. That is a big no. Don't do that. Okay? You cannot do that. This is not the 4th power of the argument. This is raising the entire expression to the 4th power. We do want to think about this as chain rule. This is something to the 4th power as the outer function. So for the derivative here, I'm going to do the power rule, and you want to keep this evaluated at the original inner function, and times the chain rule. Well, the derivative of natural log of x is 1 over x. To write this as one simplified fraction, I'll just multiply this together. By the way, it is common for people to write this as natural log cubed of x, and that would be a totally acceptable way to write this, so you'll want to get comfortable with the multiple representations of that. For number 6, we are doing log base 5 of 2x. People don't identify this one properly as requiring the chain rule, but this argument is not just x. Alright, so we do have to use the chain rule here. So, the formula for the derivative of a log of some base is 1 over the natural log of the base times the argument. Okay, so this is always the natural log of the base, and this is times that argument that showed up in the original problem. On the numerator, I do need to use the chain rule. The derivative of 2x is 2. And so that's where these pieces are coming from. I'm going to just simplify this. Actually, this 2 and this 2 can reduce out because they are just constant multipliers. And so I end up with h prime of x is equal to 1 over, and I'll move the x in the front of the natural log as just a common way for that to be written. I would not mark you wrong if you did the natural log of 5 times x. However, be careful. You don't want to write it like this. This might be leading people to the idea that that's the argument is 5x, and it's not. The argument is 5. So that's one of the reasons I write that in the front of the natural log. If you really want it in the back, you would need some type of separator to make it clear that the x is not part of the argument. I don't think you're going to see it commonly written that way. Number 7. Oh, joy! Number 7, the main rule here that's happening is the quotient rule. This is where we start. We are going to start with the quotient rule. So, for the quotient rule, we start with writing the expression that was on the denominator times the derivative of the numerator. Derivative of natural log is 1 over the argument, minus the numerator times the derivative of the denominator, all over the denominator squared. I can do a little bit of simplifying here because 2 squared times t is just t, or times 1 over t is just t, minus, I'll put the 2t in the front, 2t natural log of t. That avoids confusion with the argument, divided by t to the 4th. I'm going to go ahead and factor out the common factor of t, of just t, not t squared. Oh, there we go. And I have 1 minus 2 times the natural log of t over t to the 4th, and I'm going to reduce out a set of t's to get 1 minus 2 times the natural log of t over t to the 3rd power. I'm not sure why I wrote parentheses there. They're not actually needed, but